Hello, thank you for having me at PyCon Korea 2020. It's truly my honor to present the following topic, your escape plan from NumPy and Saisang. Here is some of my information. My name is Chenling Yang, and you can find me on GitHub, CLYANG. I'm a Taiwanese and live in Taipei now, currently working for a cybersecurity company called Cycraft Japan, and I'm also a member of the machine learning team. So basically, all my daily life is dealing with millions of logs generated by a lot of endpoints in different countries. Okay, before we start, here's one very quick question for you. Let's say you have a very large NumPy array which contains a lot of floating points, and you want each element to multiply itself 8 times. Which of the following code do you think runs faster? Is it A, the power function of NumPy, or B, x times 8, or C, the most naive one, x times x, and then repeat 4 times? I'll give you 3 seconds to think about it. The answer might surprise you. It's C, the most naive one. You just use x times x and then repeat 4 times. In order to prove it, here is the result of my benchmark code. As you can see, the power function of NumPy and x times 8, they both took about 2 seconds. And for the most naive one, x times x, repeat 4 times. And then you can see it only takes 0.4 seconds. So it's about 5 times faster than previous two. But there's a catch. So unless you are doing the scientific computing which require very, very high accuracy, otherwise the result of the last one will be a very small difference than the previous two. The difference is like 10 to number of power negative 20. So I believe in most cases, you will just choose the last solution, x times x, and then repeat 4 times. Okay, let's move on. Why not Saisang? If you ever have the NumPy code performance issue and ask your friends, colleagues, or teachers how to improve it, most likely the answer you will get is like, why don't you try on Saisang? So in this slide, I will give some pros and cons regarding to it. First, let's take a look at advantage. If you are using Saisang, and of course, you can utilize a lot of third-party C libraries. And normally, C code runs much faster than the Python code. And also, Saisang allows you to release the global interpreter lock, or called GIL, which means that your multi-threaded program can be run much faster than existing one. And also, you can still have the runtime check for the common problem, like the boundary check or some error handling, and which will handled by the upper layer Python. And then last, the Saisang syntax is very similar to Python, meaning that you can learn it in a very short amount of time. But also, it has some disadvantage. The first thing I can think is that you have to handle the memory by yourself. So for example, if you are using malloc in your Saisang code, and then you have to use this memory by yourself and then free it after all. And you have to do it all by your own. Otherwise, it might cause some very serious memory leak. And also, to get the ultimate performance with Saisang, to write the C code and the low-level intrinsic cannot be avoided. So no matter what, if you want to get the best performance, you have to write the C code. And trust me, it's really painful. It's just something like it. And why do I know it? Because the code you see is wrote by myself. Great. Let's have a look to today's example. This example will use as a benchmark code for the rest of the talk. So let's have a look. If you are not new to machine learning, you must know what softmax function is. The formula is just like the one on the screen. And don't worry, I'm not going to explain it in a mathematical way. All you have to know is that it's a number divided by the sum of a lot of numbers, and that's enough. And you might think, the formula itself looks very easy and it shouldn't be very hard to implement in Python. And yes, you are correct. But if you try to implement with the formula on the screen, you will easily encounter the numerical problem. In computer science, we call it the underflow or overflow issue. And on the next slide, I will give you an underflow example. So to avoid this kind of situation, a trick called the log sum exponential will be used. Now, here's the example of underflow. Let's say the sum of this part of the denominator is 13421778, and the last part is its reciprocal. And what will happen if we are trying to add them together? Here's the benchmark code. As you can see, I set variable a to 13421778, and then try to plus it with its reciprocal. And here's the result. As you can see, it's exactly the same as a. It's quite shocking, right? This effect is called underflow. You might think this is not a very big deal, but if you are doing a scientific calculation like Markov chain, the input data is a list of very small probability. And just like my example on the slide, after specific position, the probability will not be counted, which will cause very large error in your final result. So as I mentioned in the previous page, this problem can be solved by a simple trick called log sum exponential. And the formula is just like the one I show on the slide. And the result of this formula will mathematically equivalent to the softmax function. And don't worry again, because I'm not going to prove it in the talk, but the answer can be easily found on the internet. So in order to prove it really works, here is another example code. As you can see the final result over here, you can see the very little difference between this one and the previous one. So the smaller value is not caught or avoided, which will result in a more accurate result to your final answers. Some of you might ask, SciPy already has this function, why would you rebuild your own wheel? The answer to that is SciPy's function is built for general purpose usage, meaning it will perform a lot of checks to make sure input and output data is well handled. But in a real world scenario, you know what your data is, so you can rewrite the function based on your data. Not only you can remove a lot of checks, but also it gives you an opportunity to apply third-party boosting solution to improve your code performance. Today's case, I will assume the input data will be only one-dimensional array, and then I will try to apply 3 different solutions to the example I just mentioned before. Okay, let's moving on. How do we implement log sum exponential in NumPy? As I mentioned before, all my input data will just be one-dimensional array, so log sum exponential can be implemented as follows. As you can see, it only took 3 lines of code to finish. It's quite easy, right? Here, I'm going to leave 5 seconds to you to view the code. Time is up. So after finishing our own version in NumPy, I wrote a very simple benchmark code to compare our own version versus SciPy's original function. The result is on the right. As you can see, our version is about 0.5 seconds faster than the original SciPy's function. You might think it's only 0.5 seconds, it's not a lot. But if you need to call this function 1,000,000 times a day, it will save you about 500,000 seconds. That's quite a lot, right? Starting from here, I'm going to introduce 3 different types of solutions that might improve your NumPy's performance. The first solution will be CuPy. CuPy is an open source project developed by a Japanese company. It provides NumPy compatible ND array on CUDA, so you can utilize all your GPU powers. And also, it is compatible with existing CUDA kernel, meaning that you don't have to waste your existing file. You just need to import it, and then CUDA will run it for you. It also provides many NumPy equivalent functions, so you don't have to change your code a lot and minimize the code refactoring effect. But still, please remember CuPy and NumPy has some difference. Please check on CuPy's website to find the details difference between CuPy and NumPy. And one last thing, moving the data between CPU and GPU is very expensive. Please use it wisely. Otherwise, it might not improve your performance, but drag your performance a lot. So how do we implement log-sum exponential in CuPy? It's quite easy. All you have to do is import CuPy as CP, and then use a function underlined over here, cp.array, to convert the existing NumPy array to CuPy array. And then CuPy will does the magic for you. And here is the final result. As you can see, our CuPy version, the running time of our CuPy version is just 1.6 seconds. So it's from like 6.5 seconds to 1.6 seconds. It's pretty amazing, right? Now let's move on to the next solution, Numba. Numba is a very popular open source project that can boost your NumPy and Python performance. It is also backed by many large companies and organizations. The approach Numba uses is called just-in-time technology. Basically, it just translates a subset of Python and NumPy code into low-level machine code and runs faster. It also utilizes both CPU and GPU power. One of the best things Numba has is that it supports OpenMP, which means that you can improve your multi-threaded program much faster. The highlight of Numba is that it provides near zero code modification. All you have to do is put a decorator @JIT before the function you want to speed up, and Numba will take care of it. And currently, Numba only works best with the functions, not classes. So if you want to accelerate your classes, please do not use Numba. Otherwise, you might have a lot of issue with that. And Numba also has a very large user community, which means that if you have any problem, you can find the answer on the Stack Overflow. When talking about Numba, there are two modes you need to know. The first one is no Python no. So in this mode, Numba allows you to get rid of Python's GIL. So you can get the most of the performance from it. But not every function is supported in no Python mode. So sometimes you have to switch back to the object mode. In order to know which function is supported in which mode, you have to look up the document in Numba's website. Luckily, the document itself is very thorough, so you shouldn't have any problem to find out which one works in which mode. Finally, if you want to use OpenMP, you must use it with the no-JIT mode. So basically, you only can use it in the no Python mode. And with that, here is the sample code of the OpenMP code. As you can see, all I have to do is just change the P range to P range. And then Numba will recognize this and then trying to parallelize my code. So there's just one character change, and then I can get the most performance out of Numba. Now let's see how to implement log-sum exponential by Numba. Here's the example I wrote. As you can remember, when you're looking at the code, it's basically almost the same as the one I implement in NumPy. Yes, that's correct. They are exactly the same. The only difference between this one and the previous one is that there are two different decorators I put. So the first one is @JIT, and the second one is @NJIT, and everything else is almost the same. And here's the result. As you can see, when using the no Python mode with Numba, the performance I get is about 6 seconds. But when switching back to the JIT mode, it's about 6.7 seconds. I think it's about 0.2 seconds slower than the original SciPy functions. So here's the very big difference. If your function cannot accelerate by NumPy, sometimes it will give you the worst result. So be careful with that. Now let's move on to the last solution, Pythran. Pythran is a relatively new open source project written by a French developer. It is under very active development and has a very fast growing community. Unlike NumPy, which uses just-in-time technology, Pythran uses ahead of time compiling approach. Basically, it means that it will translate a part of your Python and NumPy code into C++, and then utilize modern compiler to compile and optimize your code into very efficient low-level machine code and runs faster. It also supports a subset of Python and NumPy functions and works on Python 2.7 and Python 3.6 through 3.8. Just like NumPy, all you have to do is put a very special decorator before the function you want to boost, and Pythran will take the rest work for you. And it also supports OpenMP, so you can utilize the full power of multi-threaded in your code. So how do we implement log-sum exponential in Pythran? To use Pythran, normally you need two steps. First, you just write the Python code as usual. So here is my sample code. The only thing you have to do is put a very special decorator, like over here is the hashtag Pythran export and then your function name, and then the data type of the input data. And that's pretty much everything you have to do. And then the rest is just like the one in NumPy. After you finish editing the file, all you have to do is compile your code. Use this very, very long command over here. Or you can take a easier one. You just use Pythran and then, which part? Over here, Pythran, and then your file name. And you will use all the default arguments to compile your code. So once you finish your code and compile your code without any compiling error, then second step is that import the compiled module to the file. So you just create another file and then import just compiled module over here. So here is the example. And then all you have to do is just call the function like you used to do in the Python. So here is the code. And the code will successfully execute it. Here is the result of the Pythran. As you can see, the result is much, much faster than the NumPy's NoPython mode. So, it's NumPy's NoPython mode. It only took 5.45 seconds to finish. It's about 1.5 seconds faster than NumPy's NoPython mode. So if you want to get the full power of your CPU, please consider to use Pythran to get the ultimate performance. So that's it. I just introduced 3 different approaches to improve your Python and NumPy's code performance. So right now you might want to ask, which is better? Before we compare, I have to tell you, all the benchmark I run in the previous slide is on a bare metal machine with the following specification. The CPU I use is an Intel Xeon CPU, and it comes with 256 GB of RAM. It also has a GeForce GTX 1080 Ti GPU. The Python version I use is 3.6.9 on Ubuntu. And all the other libraries and version information you can find on this slide. In this slide, I just put all previous benchmark results into same bar chart, so you can compare the result by yourself. The answer itself is quite clear. If you have single or multiple GPU, CuPy will be your best choice, because when you see the original function in SciPy took about 6.7 to finish, CuPy only needs 1.6 6 seconds. So that's about 5 times faster. It's just a no-brainer. However, if you don't have any GPU, don't worry, you still have the other option. So as I mentioned before, original SciPy's function took 6.7. In this scenario, I would suggest you to try NumPy first, because NumPy supports more NumPy solution than Python. So after you give a NumPy a try, you will find that in Node.js mode, NumPy can successfully compile and execute, and it gives you about 0.7 seconds faster. And from now on, you can give the Python another try. So if the same function also supported in Python, then it can give you extra performance boost. In my case, Python can work in my benchmark code. So the total execution time of Python is 5.4 seconds. So by comparing to the original SciPy's version, it's about 20% or 25% faster than original solution. Let's not bet for just change a few lines of code and get extra 20% of performance. I can call it a day. At the end, I would like to show you my own decision tree to CuPy, NumPy, and Python. Here is my decision tree. So the first question starting with, do you have GPU? If you do have GPU, then the following up question will be, do you need to use CUDA kernel, or do you need to implement your own CUDA kernel? If the answer is still yes, then I will recommend you to use CuPy. If the answer is no, then the following up question will be, do you also have the CPU computation task with your GPU? If the answer is yes, then NumPy will be a better choice. Otherwise, please stay with CuPy. If you don't have any GPU, you still have options, right? But the question itself will be very, very easy. Do you like to deal with compiler? So if the answer is no, then I would suggest you to use NumPy. So it will only give you a very minimal compiling errors. And if you are a geek and you like to deal with the compiler, compiling flag, and all the compiling error logs, and then of course Python can give you the most of the. And also, if you choose Python as the example I demoed in the previous page, and also in my real work, Python can almost always give me the most CPU power out of it. So I would suggest you, if you want to achieve the best performance with CPU, Python will be your best choice. Finally, at the end of this talk, I would like to provide 3 takeaways to you. First, if you have GPU, please try CuPy first. It's really easy to use CuPy. Just import CuPy as CP, and then call NumPy's function with CuPy. But there's one thing you have to remember. Please remember to convert NumPy's array to CuPy's array. So CuPy can help you to move the data from physical memory to graphic cards memory. Second, if you only have GPU, that's totally fine because you still have option. In this case, I would suggest you to use NumPy first, because NumPy supports more NumPy functions than Python. And I would strongly recommend you to use NumPy and its no Python mode. If your code runs smoothly with NumPy and no Python mode, then I would suggest you to try Python to get more performance. In my company's case, we can get the most CPU power with Python every time. So it's very worth to give it a try. Finally, each solution supports different numbers of NumPy's function. Luckily, each solution has a very well written and maintained website, so you can easily find the support function list on each solution's website. So just give it a look. And also, it's fairly easy to find out which function doesn't work, because normally your program will just die if the function is not supported by the proposed solution. And also, if A doesn't work, be my word. So if, for example, if Python doesn't work, you can always give NumPy a try. And in the reality, especially during my work, I always try to use a mixture of these three proposed methods. So sometimes I will use NumPy with Python or CuPy with Python. So it's all up to you. I would suggest you to give a mixture solution a try. So that's pretty much all my talk. Thank you. And I hope you stay safe during the COVID-19 pandemic.